Because the recent work with Takeshi Ikeda from Japan, we were working on some polynomials, and it's related to this Schubert calculus, which is the study of Schubert variety, which is some subvariety inside of homogeneous spaces. The most basic example is like a Grassmannian of D-planes in complex n space. And yeah, so I think there are no one here working in Schubert calculus, so like I will try to do a good introduction of what's going on with this subject, because it's related to so many different things, but then we are only looking at specific things. Yeah, so it uses a lot of different techniques, but we are looking at the same objects coming from different places. Yeah, so the Schubert calculus, there are three components, I think: combinatorics, and also representation theory, and geometry. Now, I would say I'm a geometer. I started from a geometry of orbifold, and then recently I moved to this Schubert calculus. And so those triangles, and then this Schubert calculus sits sort of among those three things. So if you go to a conference on the Schubert calculus, you find combinatorics, and then you find representation theories, and also you find geometers. And the good thing is you can talk to so many different people, and maybe if you're just beginner in this subject, and then you have to learn so many things that you can't know one thing so deeply, because you spend a lot of time learning different things. And also, like before I was working on this Schubert calculus, I was working on orbifold, and it's also a similar subject in the sense that orbifold appears in every places, but then so the hot topics of orbifold is related to this mathematical physics, like string theory, and then there you have to learn so many different things. So I think I'm good at learning so many different things, so I think this subject suit me. And so I think even when you say combinatorics, there are so many different things, so like more like it's the theory of symmetric polynomials, I would say. And then you see those Young diagrams and Young tableaus when you study symmetric polynomials. Yeah? All right. So my talk is about some formula of certain symmetric polynomial and related to symplectic linear group. Yeah? So in the classification of Lie groups, it's type C. Yes? And also, so the basic subject is basic object you study in the beginning is type A, which is general linear group or a special linear group. So the Grassmannian of D-planes in complex n space is a type A case. Yeah? So a lot of things already known in type A for the general linear group. So first I'm going to draw a big picture of what's going on with this Schubert calculus in type A. And then I'll point out, so this is where I'm generalizing to type C. Yeah, I think that's reasonable introduction. So let me start. Type A case. So let's put the number 1, 2, 3. So what kind of object we are looking at in this triangle? So in the side of combinatorics, okay. So let's fix D first. Yeah, some positive integer. And the combinatorics, you look at partition. So we usually write lambda. And so this is the set of partitions with length d. So lambda is lambda 1 through lambda d, and it's weakly decreasing. Yeah, so usually we write as a Young diagram. For example, you look at 2, 1, so that will be two boxes in the first row and then 1 box in the second row. Okay, and so I didn't fix any restriction on the number box in each row, so it could be like as large as you like. Yeah, but then I also use the notation, if you fix some n, and if I write this way, so in this case, this lambda I, the number box, is between 0, and n. Yeah? So I just draw the picture, n equal 4. No, sorry. No. This is n minus d. Okay? So n equal 4 and d equal 2 case. So I have those 1, 2, 3, 4, 5, 6 partitions. Okay? And then I'm not explaining the diagram why there are these edges right now, but let me. Yeah, I think it's time to explain. Yeah. So this partition, this behind the scene, there is a permutation of n letters. Okay, and among them, there's so. Usually we write as one line notation, right? Yes? And then among those, this permutation of n letters, there is so-called Grassmannian permutation. So the condition is up to d letters in this one line notation, it's increasing. And then also the last n minus d letters, those are increasing. So when you look at the one line notation, there's only one descent. So that's called so this is Grassmannian permutation of, say, I don't know, degree or at descent at this one. Yeah. So these Grassmannian permutation is it's one-to-one correspondent with this, the partition of at most d rows, and the number boxes in the row is bounded by n minus d. So this is what I'm writing. So it's the n equal 4, d equal 2 partition. Yeah. So it's in 2 by 2 rectangle. So this is d times n minus d rectangle. So you're looking at the partitions in that rectangle, right? And I'm just listing all the rectangles. And then there is a corresponding Grassmannian permutation. Yeah. And then how to associate is a little complicated, I think. I think I forgot to write how to make a correspondence between these two for now. Yeah. So maybe it's an exercise that by looking at those numbers, how do you make a correspondence between those two objects? Maybe if I'm supposing those people here are a combinatoric, so like you can easily come up with a correspondence. Yeah. But it's not very important right now, so let's just skip that part. And so this is the combinatorial objects we have to deal with. And then also behind those combinatorial objects, there are a little bit of algebraic object like a permutation group. And inside a permutation, the very specific permutation. Yeah. And so in larger picture, this permutation group is the Y group of general E group. Yeah. So if you change the whole setup to type C, you have to. So here, what you have to see is something similar to partition, and something. So Sn should be replaced by signed permutation in type C. So that's the Y group for the symplectic group. So you can sort of imagine what's going to happen in 15 minutes or something. Yeah. All right. So. And then we have this symmetric polynomial, and then it's very well known that it has a very distinguished basis, right? There are generators. This ring is generated by elementary symmetric polynomials or complete symmetric polynomials, but we are looking at a basis over as a Z module. Yeah, it's indexed by the partition without the bound on the number of boxes, and so there's so-called sure polynomial. Okay, and so there are several definitions by now, but one of the definitions for the sure polynomial uses Young tableau. Yeah, so let me just write a Young tableau of shape lambda, and then this is, you look at, so yeah, okay. Let me just put an example. Right? If you have a one box Young diagram, and the Young tableau is just the numbering of this box, yeah, and let's say d equal 2, and then you pick a number between 1 and 2, yeah, and then you label. So you have 1 or 2. So this is t, this is t. So in this definition, S of one box is x1 plus x2. Yeah, and then so because there's only one box, there's no definition happening here. But if you have two boxes, yeah, so in this direction, it's weakly increasing. Yeah, so 1 1 or 1 2 or 2 2. So the sure polynomial with two boxes in a row, in the first row, is x1 square, x1, x2, x2 square. So is this kind of well-known thing if you study symmetric polynomial already? Maybe first time to see? It's good, it's good. It's good if you didn't know. Right. So you can sort of guess already that if you increase the number of boxes in the first row, you're getting complete symmetric functions because it's weakly increasing. Yeah? So this is actually a complete symmetric function. Yeah? And on the other hand, let's look at the one column. Yeah? So every row has one box. So as a partition, it's 1 1. Yeah? So this it's strictly, so in this direction it's strictly increasing. So you have 1 2 only, right? So x1, x2, and then 3 boxes. Also, wait, 3 boxes. There is no 3 boxes, right? 0. Yeah, and I think it's enough, right? Okay, I can do 3 boxes, but then maybe I don't need to do that. Right? So I mean, because D is 2, it's kind of stupid, right? But you can imagine if D is, so let's say D is 3 here. Yeah, that's more interesting. Yeah? x1, x2, x1, x3, x2, x3. Yeah. So this is elementary symmetric function. Yeah. So increasing the number of boxes in the first column, it gives you elementary symmetric functions, and increase the number of boxes in the first row only, then you get complete symmetric functions. Yeah. So this ring is generated by one row sure function or one column sure function. Yeah, as a ring. But then if you collect all the partitions, it actually gives you z basis. Yeah. So this is very interesting object to study, and why is that? So let me first talk about the structure constant. Yeah. So what's the point of having a z basis? You can write down. You can ask, how do we compute the structure constant? Because structure constants will determine the ring structure. Well, ring we already know very well, but somehow the structure constants also tells you the property of the z basis you started with. Yeah. So it's natural to consider the problem of finding the structure constants. And of course, this is an old problem, and there have been worked out in many different ways. Yeah, and what's very interesting for combinatorics is this counts. This number is obtained by counting some combinatorial objects. Yeah, and then I can just give you some names, little what Richardson semi-standard Young tableau. Yeah, and also from geometry side, Knudsen and so I haven't talked about the geometry side, but the Knudsen Tao also found these coefficients from the geometry side using certain puzzles. And then I think there's something related to chess. There are so many different combinatorial objects that counts. If you count those two objects, then you get the number. Yeah, and so the corollary is that see. It's obvious corollary that this structure constant is non-negative. Yeah? And that is not obvious from the differential over there at all. Yeah? So when you fix a z basis of a z algebra, and it's just not really clear that how you make the structure constant to be positive, or more precisely, non-negative. Yeah? So this basis has very distinct property that the structure constants are positive. Yeah? And that's because you can calculate these numbers by counting some objects. Yeah? Okay. Any questions so far? Are you with me? Yeah.
Is this a number or an integer?
It's integer. Yeah? I mean, it's a Z module and it has a ring structure, so the structure constant is a Z integers. Yeah. So this element, the product is a symmetric polynomial, so you can expand this in terms of this Z basis. That's the coefficient, right? All right, but then calculating the structure constants is actually one of the biggest goal of Schubert calculus. Well, I haven't shown any other object related to this short polynomials, but in any way, if you can calculate those structure constants and then having some closed formula or combinatorial formula to calculate these structure constants, people will be very happy and respect you. Yeah. And later I'm going to so this is a formula to describe a Schur function, right? It's a very combinatorial formula, but there are other formulas to describe the Schur polynomial. And when you try to calculate the structure constants, this formula might be useful, but might be not. Yeah. So if you find some equivalent formula that describes Schur polynomial, that might be very helpful when it comes to computing the structure constants. So explicitly having a formula for the Schur polynomial in many different ways, that makes it very powerful when you try to calculate structure constants. Yeah, and I will show you some other formulas later. All right, so let's move on. It's number 2, representation theory. And let me just cite one theorem, right? For each partition, you can construct, so, okay, I think I should do this. Yeah, is the set of all irreps for SLN. Yeah, so this is a very basic fact of irreducible representations of SLN, of complex number entry. Yeah, and if you want to learn about these things, Fulton's book on Young tableau it explains very well. Yeah. Okay, and then also, so that's one fact, and another fact is the character of the lambda is S lambda x. Yeah. So this is the connection this is one of the connections between representation theory and this theory of shear functions. Yeah. Okay, so the consequence of this is you can interpret this structure constants as a multiplicity of tensor products of two irreducible representations. Yeah. So if you take a tensor products of two things, you wonder what this is, right? So these are irreducible representations, and then there's a construction described in some textbook. Yeah? And when you take a tensor product, you get another just a representation. It doesn't need to be irreducible representation, right? So but this is a representation, so it should decompose into irreducibles because you're talking about SL. Yeah. So if you decompose, right, partition. So you might have some multiplicity of the same irreducible representation sitting inside of this tensor product, and that multiplicity should be this constant, because taking a character is like it's preserved under this tensor products. Yeah. So, okay. So in the representation theory, calculating this structure constants of shear functions is really finding the multiplicity of the tensor products of two irreducible representations. Yeah, that sounds very interesting already for representation theorists. Okay, and that's all I should say for representation. There are other relations, but this might be the only thing I wanted to say today. Yeah. Okay, so I just put geometry at last because this is not a seminar for the geometry. So if you don't like geometry, then you can forget this part. But I have to talk about this. So geometry behind these shear functions, it's Grassmannian. So this is Grassmannian of D-planes in a complex n-plane. Yeah? And the fact, very interesting fact is, very deep fact is, you look at this ring of symmetric polynomials, and then you can find very natural surjection, ring surjection to cohomology of Grassmannian. So here you haven't fixed n, yeah. But then if you want to talk about the honest space, you have to fix n. Yeah? So this side you are fixing n, and this side you're not fixing n. But then there is any for which if you fix any n, then there is always a natural surjection in the sense that there is a relation among. You can take actually a projective limit or inductive limit of Grassmannian, just sending this n to the infinity, and also you can take the projective limit of a cohomology ring, taking n to infinity, and this ring surjection is natural with respect to that limit. So actually, you can also you can actually think of this ring of symmetric polynomial as a limit of cohomology ring of Grassmannian. That sounds very amazing, right? But then, if you have studied like algebraic topology in the very first course, like Boden 2, you would know why you're looking at the symmetric polynomials. It's about the theory of Chern roots of tautological bundle over Grassmannian. So this topic is a very good example for first course in algebraic topology. But anyway, so how do I interpret those x1 to xd in geometry, right? So before that, I have to talk about tautological sequence. So E is like a trivial bundle over Grassmannian. So you're looking at complex n plane, right? Inside of that, you're looking at d planes. So you take this complex n plane, yeah, and then take just direct products as a trivial bundle, right? And here, inside of this trivial bundle, there is a tautological bundle. So for each point in Grassmannian, it's a d plane. Yeah, this bundle, the fiber, is the plane itself. You know what I'm saying? Yeah? So you take a plane from Grassmannian, so this is D plane, right? And so the fiber at this point in the Grassmannian is V itself. So this is tautological vector bundle of rank D. Yeah? So this bundle naturally comes with the Grassmannian, and it plays a very significant role when you try to study, particularly when you try to study some algebraic topology of Grassmannian, yeah, because of the characteristic classes theory. Yeah? And then there's also a dual version of that, a quotient tautological bundle. So this sequence, we usually call it a tautological sequence. Yeah? And so this is really based on the convention, but you can think of x1 through xn, those parameters, as Chern roots of S dual. Yeah? So be careful, x1 through xn, those individual parameter, is not an element of a symmetric polynomial. Right? And also the Chern roots of a vector bundle, it's not in here. Because you use this splitting principle that you pull back this vector bundle to a space where you can split into line bundles, and the Chern classes of those line bundles are called Chern roots. Yeah, so that is like very basic algebraic topology. Yeah, excuse me. All right. So and also when you look at this sequence, you have a relation. The total Chern class of those, so this total Chern classes of S and Q is equal to total Chern class of the one in the middle when you have a short exact sequence. And this is trivial bundle, so it's just one. Okay, and it's also the very basic fact that this Grassmannian cohomology ring is generated by Chern classes of quotient tautological bundle. Yeah, and it's so because or I think the Chern classes of tautological bundle. Okay, and let me just put a dual here. It's just plus minus difference. Yeah, and then so if you think of those x1 through xd as a Chern roots of a dual of tautological vector bundle, this is really elementary symmetric polynomial of x, and this is elementary symmetric polynomial of x. Yeah, and because of this relation, you can think of this as so this is complete symmetric polynomial. So for Q, it's complete symmetric functions, and then dual of S, that's elementary symmetric functions. So either way, it's generated by symmetric polynomials. Yeah, so that's where this surjectivity actually comes from. Okay. And so I'm keep going with the fact there is a surjective ring homomorphism, and there is this Schubert polynomial. And the Schubert polynomial, where does it go? There is some geometry behind this Grassmannian, and that is it's a class of Schubert subvariety. Okay, so this is the connection between symmetric polynomials and the Schubert calculus. So the Schubert polynomial actually goes to the class associated to a subvariety called Schubert variety. Yeah. Okay, so of course, this lambda sits inside of without any restriction on the number of boxes in a row, but this we are already fixing n this side, so this lambda has a restriction on the number of boxes in the rows. So actually 0 if lambda is not the number of boxes exceeds n, then n minus d, then it's going to 0. Yeah, it's like a projection. Yeah, projection when the number of boxes exceeds n minus d. Yeah. But still, it's a ring homomorphism. Yeah. So let me stop here and think. Right. What is the structure constants of the cohomology ring? So if you are algebraic geometer, you can do intersection theory of like a Chow ring. Right? So you take two subvarieties and then you intersect transversely, and then what it's going to be a union of other subvarieties, yeah, and the multiplicity of that will give you those structure constants. Yeah, so intersecting two varieties. So basically, if you have a basis of a cohomology ring, you have a collection of subvarieties, so that associated classes give you a z basis of a cohomology ring, and then the structure constants with respect to that is you intersect those two subvarieties after you move so that they are transversely intersected, and then intersections you have some weird spaces, but then you also deform them into the list of subvarieties, and then you look at the multiplicity for each subvariety that form the z basis. Yeah. So calculating that structure constants of the symmetric polynomial ring with respect to Schubert polynomial, it becomes very geometric now. You intersect those two Schubert varieties and then decompose the intersection into the smaller Schubert subvarieties, and the multiplicity is given by those constants. Yeah. Okay, I think I just convinced enough that this number is also geometric. Yeah? Okay. Okay, I think I talked about this combinatorics and the representation theory and the geometry. So it's related to so many different things, but so people are trying to get these constants so that if you understand these constants very well, the impact you can imagine in other areas is huge. Yeah? So, I just started to work on this Schubert calculus maybe 2 years ago. So I'm just very beginner, and like calculating structure concepts is like my dream. Right? It's very big problem, and like easy problems already solved, right? I think. So, but of course I started with the type C cases, and my goal, the type C cases, those structure constants are not calculated nicely yet. So it's one of my goals, pursuing this Schubert calculus. So, but before you calculate structure constants, still understanding this Schubert polynomial is important, because so this is one of the formula, the closed formula that gives you a Schubert polynomial, but there may be other formulas. And then if you have different formulas, maybe when you try to calculate the structure constants, it helps. Yeah. So getting a good formula for those polynomial is actually very important problem called Gambelli problem. And this is a particular kind of problem. So it's a particular kind of attitude when you try to find a formula, right? So the attitude is it's the trying to find a closed formula for those Schubert polynomial, or the generalization of that, in terms those one row cases. Yeah. So in this case of symmetric polynomials, those one row Schubert functions, those are complete symmetric functions. So it generates the symmetric polynomial as a ring. Yeah. So theoretically, this S lambda should be written in terms of those one row Schubert polynomials, and then getting a closed formula for these Schubert function in terms of those complete symmetric function is actually called the Gambelli theorem already, right? Because we have the formula. So let me just write it out. So this is theorem. Yeah, it's written by a determinant. Yeah, And the entry of the determinant is h lambda I plus j minus I. ij varies from 1 to d. Yeah? And so I'm not really sure why this is called Gambelli. Because this particular formula is called Jacobi-Trulli. So I think, so I don't know, this is Gambelli, or it's also, there are named Kemp. Yeah, so I think, as I said, this Schubert calculus is in a different areas, right? So from different directions, they prove the same formula. So they have so people, if you look at these as polynomials, then it's called the Jacobi-Trulli formula. But then you can replace this by Schubert varieties. Right? You just push this into cohomology ring, and then if you push this into cohomology ring, I think it's called Gambelli or Kemp-Laxov. I think originally it's Gambelli, but then a slightly more general formula obtained for the Schubert varieties, it's Kemp-Laxov. Yeah? And it's actually in this formula, the generalization is like you describe Schubert variety as the degeneracy loci of some vector bundles. Yeah. So. Okay, this Gambelli formula is the basic formula I have in my mind, and I'm trying to generalize this Gambelli formula for other cases. Yeah, because writing it as a determinant of something it looks nice. Yeah. Okay. All right. So now you know what I'm trying to do. What I'm trying to do is to generalize this Gambelli formula for other cases. Yeah, and when I say other cases, not only type C, but we are talking about the cohomology case, right? But then there is analogous story for equivariant cohomology, and then not only talking about cohomology, but you can also talk about K-theory. Yeah, and I think Gambelli problem for K-theory it's not really discussed well because people are not sure. Yeah, yet. And then also you can go out of the world of type A, you can go to type C. And then there, I think, so the point of my talk today is you should replace this determinant by Pfaffian of matrices. Yeah? But anyway, so first let me just talk about equivariant setup, because that's what I was doing for type C. Yeah? So what's the generalization? So you have symmetric polynomials, right? And the target of this surjective ring homomorphism is going to be equivariant cohomology. And equivariant cohomology, it's always the algebra over polynomial ring, T1 through Tn, which is the cohomology of class-Wien space of a torus that acts on the Grassmannian naturally. So this torus has n dimension, and it acts on this ambient vector space C to the n. Yeah? So that gives you an action of that torus on this Grassmannian naturally. And then so how do you degeneralize this side? You just add the t variables. Yeah? The infinite t variables, because if you fix n, then you have t1 through tn, but then before that you need infinite number of t variables. Yeah? So there is analogous Schur function. It's called factorial Schur, and then that goes to equivariant Schubert classes. Yeah, and then you can also talk about equivariant structure constant, which is an element of the polynomial ring of t variable. Yeah. And then here we also have a little Richardson counting, and also Knudsen and Tau puzzle counting. Yeah, we're not getting a number, but then to get some polynomial of t as a structure constant, you can also count some combinatorial object. Yeah. So this generalization of these counting problems for equivariant comb, it's already done in many cases. Okay, and all right. So this is non-equivariant Gambelli formula. So you write a sure polynomial as a determinant where the entries are complete symmetric functions. So if you want to generalize this to this factorial sure functions, you need some generalization of this complete symmetric functions involving some t variables too. And then there is this shifted complete symmetric functions. We define this as, it's easier if you define this as a generating function. Yeah. So the generating function of, the notation is you have degree r, and then there is upper index L. Yeah. So this L is like the involvement of t variable. There are t1 through tl will be involved in this shifted complete symmetric functions. Yeah. So L is fixed. Yeah, and then you collect all the degree. Yeah. This will be. So there are parts that comes from x, right? So what's the generating function for complete symmetric functions? Yeah. Right? The generating function for the elementary symmetric functions is, right? This is elementary. So if you look at each degree, it gives you elementary symmetric function. What about the complete symmetric functions? That will be 1 over 1 minus x1. Yeah, if you look at each degree, it gives you complete symmetric functions, right? So that is actually a very basic thing. And yeah, so you have this, the usual part, and then there is some t involvement that is t minus L. Yeah? So I forgot to put u here. Yeah? So the coefficient, so if you expand the right hand side as a power series, yeah, and then you look at the coefficients of UR, that is this HRL. Yeah? And there is a beautiful generalization of this Gambelli formula using this shifted complete symmetric function. So this factorial, this is, right? So the degree will be the same. Yeah, but then you have to choose a correct upper degree. Yeah, and this will be, I forget this number all the time, lambda I minus I plus d. Yeah. So upper index is just the involvement of t variables, right? So from equivariant case to non-equivariant, you can just make those t variables to be 0. If you set t equals 0, then you recover non-equivariant formula. So if you make those t to be 0, then it just complete symmetric function. So you just drop upper index. Yeah. So if you just drop upper index, you just recover the original Gambelli formula. Yeah. So this is you can find this in the McDonald's book, McDonald's formula. And also in the geometry side, Lakshmi Bai and Lagaban and Sankaran proved a formula which is very formally equivalent to this formula. It's just a matter of just changing a little bit of coefficients. Yeah? Okay, so I have like 15 minutes. So this is the introduction, but I think it's okay, right? Yeah. So this is what's happening for type A, and then I want to do everything for type C. And so the today's so what my work with Professor Ikeda was we completely generalized this Gambelli formula for equivariant case for type C. Yeah. All right, so type C, what happens? You are looking, so as a Lie group, you're looking at symplectic group, and if you want to just focus on the Grassmannian, right? So the typical Grassmannian for type C is just the Lagrangian subspaces. So this is Lagrangian subspaces in C to the 2n, and C to the 2n has a standard symplectic structure. Yeah, but so this is, we call it maximal case. Yeah, because we basically, I mean, there's no freedom for the degree, the dimension of the subspace if you just say it's Lagrangian. But then non-maximal case, the standard notation is this n minus k isotropic Grassmannian. So it's the n minus k dimensional isotropic. So isotropic means that, so you have a symplectic form, right? You put two vectors from this subspace, it's always 0. That's isotropic condition. Yeah. So it's always the dimension is always less than half of the dimension of the symplectic vector space in the maximal case and non-maximal case. And so because of, so this indexing is very confusing because people use different indexing. So in our setup is this, here is k. K you can change from 0 to k n minus 1. Yeah. So this is k. We call it k Grassmannian, or isotropic Grassmannian. There are many names. Yeah, and in particular, if you choose k to be 0, then you recover Lagrangian case. Yeah. Okay. I don't think I can finish. Should I? Okay, I will skip a lot of things. At least I want to show the formula. Okay, and so I have introduced shifted complete function. So this was the piece where you can write the show function as a determinant. So this will be replaced by this a little bit complicated things. So you have now three indexes, and the generating function. So here, fix k, and this is important because you are looking at a specific isotropic Grassmannian, right? And then also once you fix L, then you can write. So I'm fixing k all the time, so I drop k already. Yeah. So now you look at the generating function, and this will be. So this is the something quite different from type A. You have the now right x variable. I think I should have talked about this L yet, but I think it's okay. Right. So then you have. So we fixed k already, right? So you have this. And then now this upper index talks about this equivariant parameter. So, right, where is it? Yeah. So let's just define this so that we have some pieces to describe what's analogous to Schubert polynomial. And then having said that, this is the fact. So actually t equals 0 case, it comes from Billy Hyman, and then equivariant case, then t non-zero case. So the this is non-equivariant case, and then equivariant case is given by my collaborator Ikeda and Mihao Cher, and Naruse. So they defined some polynomials that represent those Schubert classes for the type type C. So the ring surjection, it's going to be generated by these things. So let's just separate t variables already. So like set L equals 0, and then you have those pieces, right? And then you're fixing k already, yeah? And then you collect all the degree. And then it's going to be a ring over a polynomial ring of t. And then this surjects to equivariant cohomology of n minus k dimensional isotropic subspaces. So, and then here you have some polynomial there, which goes to equivariant Schubert classes. Yeah, and then this lambda. So what is this lambda, right? So this, so this is k strict. The replacement for the partition is k strict partition. So what is this? This is, so you have some rectangle where this strict partition sits in, and then the first k row, so this part may be non-strict, but this part strict. Yeah, so if you write this lambda as lambda 1 through, so lambda 1 through lambda m. Yeah, so if this lambda is less than or equal to k, then it's like a usual partition, it's weakly increasing. But then if you go beyond k, then it has to be strictly decreasing. So too strict, you can have something like this. Yeah, but then, so this is okay, but then it's not okay. Yeah, because the second row and third row, the number of boxes goes beyond 2, so it has to be strictly decreasing. Yeah. So indexed by this k-strict partition, there's some polynomial here, and then it goes to corresponding Schubert variety in. I'm skipping a lot of things, but I'm just trying to convince that there is some polynomial defined in this kind of symmetric polynomial. It's not actually a polynomial because you have this part. Yeah, it's symmetric function. Yeah, so there is some symmetric function in that ring, and that represents cohomology ring and the Schubert classes. Yeah, and the goal is how do we get the formula, the closed formula for that. Yeah, in the last 5 minutes, I will write the formula. Okay, so this is the theorem, and Ikeda and me. So you have basically 3 parameters. Yeah. So t is equivariant parameter, so I put in after the bar, yeah? And so it looks very simple, right? It's very short, and I think I need 4 lines to define this. Yeah, just a notation for how to read. So the Pfaffian is defined there. Yeah. So the one term case, it's just what it is, and then 2 cases you compute that some term alternate sum with a change of degrees, and then after the number of slots inside more than 3 or 4, then odd or even is differentially different, but the point is it's defined inductively. Yeah? So Pfaffian is fine, it's over there, and actually there are only 3. So now you have to understand those indexes and this summation thing. Yeah? And chi 1 through chi n minus k. Okay, I forgot to write about. So this is k strict partition. Yeah, there is one-to-one correspondence with a k Grassmann signed permutation, and in the one-line notation, it's like you have v1 vk, yeah, and zeta s, and then u1 the u1 n minus s minus k. Yeah, so the signed permutation is just the permutation of signed n letters. Yeah, and then it's signed permutation, so minus I if A goes to B, and then there's a plus minus, right? And then if you set minus A, so A could be positive or negative, right? But some signed number. And then if you multiply minus 1, then it has to go to the image is also multiplied by minus. So it's a permutation of signed n letters, but then there's some restriction like this. It's called signed permutation. And then in this case, there's a one-line notation. So
each letter occurs both as a plus and a minus in the permutation.
Yes. So in that case, in this signed permutation, if you just specify where 1 goes to, if you just specify the image of 1 through n, then minus 1 through minus n is already determined. Right? So that is this. And then the condition for this K Grassmann signed permutation is, so the first K letters are increasing positive number, and then the rest, it could be mixture of plus and minus, but then still it's increasing. Yeah. So for example, 1, 3, 2, 1, 2, 3, 4, 5. Yeah. So the bar indicate descent. Yeah. So on the left, on the right, it has to increase. Yeah. But then K Grassmannian means that this 2 numbers in the beginning, it's positive and increasing, and then the rest, the sign doesn't matter, but it just makes sure it's increasing. Yeah. So you have this correspondence between K strict partition and the signed permutation, and I had to talk about this because this upper index is it's determined by these part. Yeah? So zeta minus 1 through zeta minus 1. And then here minus u1 minus u something. Yeah. Well, n minus s minus k. Yeah. Okay. And then so d lambda. Once you define this chi, so this chi governs everything. Right? Once you define chi, this d lambda is just a collection of I and j, 1 through n minus k. Yes, and then chi I plus chi j is negative. Yeah, so you just collect those pairs. Yeah, and then you take any subset in this summation, and this subset will determine this shifting of the degree. Yeah, and this shifting of the degree is determined by this subset, but it's just a number of occurrence of a particular pair involving this S. So if S is in the first slot in the pair, then it counts as 1, and then if I happens in the second slot of the pair, then it counts as -1. Yeah? Alright, so you just have this and then just put that in the Pfaffian, and voila, that's the formula. Yeah? And somehow it's, yeah, so that's...
What is the... I missed what is the lambda? D of lambda.
D of lambda. So, okay, so it's lambda is here, right? So lambda determines sign permutation. So lambda and the lambda are 1 to 1. Yeah, so K-Grassmann permutation. And then you look at the last n minus k entry, then you get... So actually, so there's of course there are a lot of work behind this thing, right? Not my work, but the other people's work. So actually, when k equals 0, the non-equivariant one is by Pragats, and then the equivariant version of k equals 0 is given by Kazarian and also Professor Ikeda from Japan, and then there's Book and Kresh and Tambakis. Those three people actually worked out non-equivariant case for general K-Grassmannian case, K non-zero case. And then their formula is in terms of so-called raising operator, if you have heard the name. Yeah, so it doesn't look like this, but then their formula is just formally equivalent to this one after you calculate something. Yeah. But this formal equivalence has nothing to do with all the content of these things. It's just the formal equivalence. So they have non-equivariant one. And Tambak's students, Wilson, actually worked on this project in her PhD thesis, and then she got the conjecture. So the conjecture is actually written in terms of raising operator, but we can actually show that conjecture is equivalent to this formula. So Bookquest Tambakis has this raising operator formula because they have to use this Shibari rule. It's the kind of product rule that sort of determines all the products in this cohomology ring. So, and then they use some uniqueness theorem to show that this raising operator formula gives you the Schubert class or this polynomial. And our method is just completely different. We use something called a left divided difference operator, and that is also used to define those polynomials actually. Yeah. And then, so they have this some uniqueness theorem. If the polynomial satisfies some compatibility condition with the left divided difference operator, then those polynomials are unique. And then we just look at this expression and then show it's compatible with the left divided difference operator. And then, so we have the claim that this is equal to the Schur polynomial. And yeah. All right, so I tried. Okay, 1 hour. Thank you.